How do massive metal machines, weighing literal tons, just float above us in space for years without falling? I mean, every single day we're using the internet, we're relying on GPS to get around, we're checking the weather, and we barely give a second thought to the fact that all of this data is being beamed down from objects flying through the cold void right over our heads. It honestly looks like magic. But the truth? It's an incredible, razor-thin balancing act of physics, gravity, and extreme speed. So today, let's jump right into this explainer and decode how satellites actually work and the mechanics that keep our entire modern world connected. So the most logical question you can ask right off the bat is, how do they not fall? We all know how gravity works, right? Earth's gravity is constantly pulling everything toward its center. You hold something heavy up high, let it go, and boom, it crashes to the ground. That is just the inescapable rule of living on this planet. So why don't these multi-million-dollar space machines do exactly the same thing? How are they avoiding that fate, and why aren't they just plummeting back down on our heads?
Well, here is the ultimate twist. Satellites aren't just hovering in zero gravity. They aren't magically suspended or floating on their own up there. They actually are falling, continuously. Every single millisecond of every single day, gravity is pulling them straight down toward Earth. They're in a state of perpetual freefall. It's a lot like that feeling you get when a roller coaster drops, except the drop just never ends. Sounds terrifying, right? By all logic, they absolutely should crash, but there is one crucial detail that changes the whole game.
To achieve orbit, you basically have to throw yourself at the ground and completely miss. A satellite isn't just dropping straight down. It has immense forward momentum pushing it sideways perfectly parallel to the planet. It's this continuous, massive sideways movement combined with that downward pull that creates the orbital magic. See, when a rocket launches a satellite, it doesn't just go straight up. It turns and accelerates horizontally to build up an unbelievable amount of sideways speed.
Think of throwing a baseball. If you throw it normally, it curves and eventually hits the dirt. But the Earth is a sphere. So imagine you're standing on a massively tall mountain, way up high above the atmosphere where there's absolutely no air friction to slow things down. If you threw that ball incredibly fast, something amazing happens. It falls, sure, but because it's moving sideways at such an extreme velocity, the curved surface of the Earth actually drops away underneath it at the exact same rate. It's falling, but the ground literally keeps dodging out of the way.
To put that kind of speed into perspective, the International Space Station travels at a mind-bending 8 kilometers per second. That is nearly 28,000 kilometers per hour. We're talking dozens of times faster than a bullet. That staggering velocity is the exact speed required to maintain that perfect, delicate balance between falling and missing. This speed is literally the lifeblood of an orbit. If they slow down even a fraction due to something like atmospheric drag, gravity wins the tug-of-war and they start to spiral right down and burn up in the atmosphere.
And depending on their speed and altitude, satellites basically live in different lanes, with each serving a very specific purpose. Low Earth orbit, or LEO, is that fast lane closest to Earth where gravity is the strongest. This is where you've got Starlink satellites zipping around giving us low-latency internet. Move up higher to medium Earth orbit, and you find the networks powering our GPS. Go all the way out to about 36,000 kilometers, and you hit geostationary orbit. At that incredible distance, the satellite's speed perfectly matches the Earth's rotation, so it looks like it's just hovering in one fixed spot, which is absolutely perfect for beaming TV signals to dishes that never have to move.
Once these incredibly complex frameworks of instruments, sensors, and antennas find that perfect balance in the vacuum of space, they become powerful tools for humanity. They're essentially our eyes from above. Meteorological satellites, for instance, are out there constantly monitoring global cloud systems, recording ocean temperatures, and tracking weather patterns. They identify massive hurricanes long before they ever threaten a coastline, giving us the advanced warning we need to save lives.
But mostly, communication satellites act as giant flying relay towers. Because the Earth is curved, a radio signal sent from New York straight to London would just shoot right past the horizon and off into deep space. The planet literally gets in the way. So instead, we beam the signal straight up. The satellite catches it, cleans up any static, vastly amplifies the power, shifts the frequency, and then beams it right back down as this massive footprint, instantly connecting huge isolated areas of the globe all at once.
When that invisible beam hits your house, highly specific hardware takes over to make that connection totally seamless. An outdoor component called an LNB basically acts like a funnel. It catches that weak, high-frequency space signal bouncing off your dish, safely lowers the frequency, and passes it through a cable to your indoor modem. The modem then turns that radio wave into the actual video you're watching right now. And when you upload data, the whole process just reverses. A component called a BUC acts like a high-powered megaphone, amplifying your digital requests and shooting them right back up into space.
But obviously, satellites do far more than just bounce the internet around the globe. Think about your personal navigation for a second. How exactly does a machine falling through the cold void, thousands of kilometers away and moving at thousands of kilometers an hour, know exactly what street you are standing on? How does that pulsing blue dot on your smartphone's map actually work?
It all boils down to a mathematical process called triangulation. GPS networks consist of dozens of satellites that act like ultra-precise lighthouses. They are constantly shouting their exact orbital location and the highly precise time out into the void. Your phone doesn't actually transmit anything back to them, it just listens. By touching time-stamped signals from at least 4 different satellites at the same time, your phone calculates the microscopic time delays between when those signals were sent and when they were received. Using the speed of light, the chip in your phone simply runs the math to pinpoint your exact coordinates.
Now, this process requires an extreme level of precision. To measure time accurately enough to locate you within mere meters, satellites carry hyper-accurate atomic clocks on board. But here is the absolute craziest part of all this. Because these satellites are moving so incredibly fast, and because they are further away from the intense gravity of Earth, time literally moves differently for them. Engineers actually have to program Einstein's theory of relativity into the satellite systems to correct these tiny time dilations. If they didn't, your GPS would drift by kilometers every single day. So yes, Einstein is literally helping your phone navigate traffic.
When you really step back and realize the sheer mechanics of what's happening above us, it's pretty humbling. Think about it. Global shipping lanes, commercial plane navigation, international banking systems, the entire backbone of the internet, even just your ability to order a cab. Our entire highly connected modern world relies absolutely on this invisible infrastructure of machines continuously falling through the dark and missing the ground. It is a highly precise, mathematically perfect, yet incredibly fragile balance that keeps modern civilization moving forward.
So, the next time you look up at the night sky, remember the invisible physics keeping our world completely connected. It's not magic, it's just brilliant science, the ultimate balance of gravity, speed, and exact calculations. If you want to keep exploring how space and technology actually work, hit subscribe to Code of the Universe. We're here to make the complex simple, decoding the mysteries of our reality one concept at a time. Keep exploring, keep asking questions, and we'll catch you in the next explainer.